Nice. Okay, so I'm Gustavo Bejar. I'm a PhD candidate at Michigan Tech, and I'm also the host for this CONVERSE webinar series. So before we start, I want to direct you to our website, converse-er.org, so you can get more information about CONVERSE the Converse Center, and to access recordings from our previous webinars. And I also want to announce our speaker for our next session. That's going to be Kyle Dayton from Cornell University. The title for her presentation is still TBA, but just know that the next session is going to happen on March 25th at 4 p.m. Eastern Daylight Savings Time. And remember, we are now in UTC -4 time zone. So we're going to be starting an hour early in case you are outside of the US. Just want to mention that because we've been having some issues with people in different places adjusting for time zones. And with that, I'm very excited to introduce our speaker for today. This is Claudia Corradino. Claudia is a researcher at the Etna Volcano Observatory by the National Institute for Geophysics and Volcanology in Italy. And um, let's see. So Claudia, she graduated with a neurotechnology engineering degree in 2014 at Imperial College in London, and later got her PhD in 2018 at the University of Catania. Her research focuses on artificial intelligence for volcano monitoring from space, and she's currently involved in developing AI-based solutions for the volcano operational thermal data products for the NASA Surface Biology and Geology mission, which is very cool. So in this webinar, Claudia will show how artificial intelligence plays a key role in the field of volcano monitoring in extracting meaningful information and gaining new insights from large volumes of satellite data at different spatial and temporal solutions. So with that, I'm happy to introduce Claudia. Welcome. Thanks again for being our speaker for today.
Thank you, Gustavo. Thanks. I'm sharing the screen. So, okay. Okay.
Yeah, that works.
Perfect. So, hello to everyone. I will try to give you a brief overview of how artificial intelligence can help addressing some problems for volcanic hazard monitoring and nowcasting. So I will try to give you a brief introduction on the main topic. So I work at INGV. So I'm a researcher at Etna Volcano Observatory. INGV is a research institute that focuses on both research, monitoring, and also surveillance. And we have INGV sites all over Italy. And of course, we monitor volcanic activity. So volcanic eruption can pose several hazards to communities living at the edge of active volcanoes. We know that volcanic inner structure is not accessible. Lots of mechanisms are partially known. So it's very important get data, external observation that are needed to understand better volcanoes. Specifically, if we monitor using different kind of observation of data, and we can actually detect sign of changes before an eruption start through ground deformation, for example, gas emission, thermal anomalies. Then once an eruption starts, we can follow the eruption by using different parameters, and we can actually characterize all the volcanic phenomena taking place, and we can, of course, predict all the forecast, the different kind of scenario that can happen. So understanding volcanic behavior through observations and data, it's fundamental to track unrest sign and also forecast volcanic eruption. But data are fundamental. So data-driven science is the fourth paradigm of science, because we move from empirical science to theoretical science to computational science, and now we are in the big data driven science. So data can be used not only to monitor but also to retrieve knowledge from data, and we adopt this novel paradigm to solve volcanic hazard problems. So We do this particularly by using satellite data, because satellite data offer a synoptic view of the Earth at a variety of spatial, temporal, and spectral resolution. And we monitor continuously through satellite data, and we have huge amount of heterogeneous observation, and we need advanced techniques to interpret automatically the data and also to better understand and retrieve knowledge from this. So the two main pillars for us is our satellite data stream, so open access satellite data from ultraviolet to infrared to radar, and data-driven approaches, so advanced artificial intelligence techniques. So I will try to, so the presentation is divided into three main sections. One is more about satellite remote sensing for volcano monitoring. The second part about artificial intelligence. The third part is some example on how we can use artificial intelligence for volcanic hazard monitoring from space. So, as many of you probably know, we have two main kind of satellite sensor that can be used. Satellite sensor on board of geostationary satellites that move together with the Earth, so allow higher temporal resolution with lower spatial resolution because orbit farthest from the Earth. And the polar satellites that actually give higher spatial resolution information but lower temporal resolution. And on board of this satellite, we can have active and passive sensor. So passive sensor do not emit radiation by themselves, they just receive radiation from external source like the sun or the emitting ground. And active sensor emit radiation by themselves and receive back and measure what is they received back. And the frequency, of course, can go from ultraviolet to radar. So passive sensor, I won't go into the details, of course, but I don't know how many of you have knowledge about this, the background. So of course, the sensor radiance, this radiance the sensor receive, the passive sensor receive, it's given by different, receive different kind of contributions. So the upwelling radiance, the radiance emitted by the atmosphere, a portion of radiance that are welling from the atmosphere that reach the ground and is reflected back, and the most important portion for us, that is the emitted radiance. So it depends on the temperature of the ground, and so if we have lava flow, for example, based on the temperature, we have the emitted radiance that actually is the biggest contribution that receive the sensor coming from the ground, and that follow the Planck law and the Wien law as displayed here. And the volcanic features that we can measure by using passive sensor are different, are features related to the radiant emissions. So actually we can monitor the volcanic radiative power thanks to this kind of infrared information that because based on the temperature, we have different contribution in different spectral wavelength. And so thanks to the radiant emission, we can actually not only map volcanic lava flow, for example, by using high spatial resolution sensor, but also monitor how the effusive rate change during an effusive activity and calculate the volume, for example. Then if we use other information, even the visible information, we can actually measure, we can actually monitor the spectral signature of the surface. And the spectral signature of volcanic eruptive deposit may tell us if a lava flow is young or old, as you can see in the bottom left graph. Depending on the spectral signature, we can discriminate between the two. And also, thanks to the spectral signature, we can actually detect distinctive feature between in the volcanic cloud between SO2, if it's composed by SO2, ash, or ice, for example. So we will see some study case related to this content. And also we have active sensors, so we have synthetic aperture radar on board of satellites like Sentinel-1 that allow us to actually monitor the resurfacing process of lava flow, because depending on the amount of backscattered signal that is received back by the sensor, by using post-eruptive and pre-eruptive images, we can actually detect if something changed. So the resurfacing process, like lava flow or big deposits. And of course, each satellite sensor has its own spatial, temporal, spectral, and radiometric resolution. So spatial is related to the size of the pixel that represent an area of the surface. Temporal is how frequently satellite can provide observation. Spectral is the ability of the sensor to be shared among wavelength. And radiometric, the amount of information in each pixel, so the number of bits that represent the energy. And based on the kind of our goal and on the activity taking place, we should use one satellite sensor or one other. For example, if we focus on spatial accuracy, if we want an accurate mapping of a lava flow, we will need high spatial resolution, low temporal resolution data. While if we are focused on temporal accuracy, like if we want to monitor a volcanic activity rapidly evolving in time, of course we need satellites, geostationary satellites that have higher temporal resolution but low spatial resolution. Of course, we have lots, as we said before, heterogeneous and different kind of satellite, lots of data, and usually the process of retrieving information, interpreting the content of these images is time consuming. That's why artificial intelligence algorithms may help us to process this big amount of data, to interpret it automatically data, and to retrieve knowledge from data. So artificial intelligence actually was defined in 1955 for the first time, that it's like the science and engineering of making intelligence machine. And the goal is trying to let a machine perform tasks that usually are done by humans. The first approaches were knowledge-based. So they require the expert to input exactly the rules that need to be taken to get the final goal, to get to the final goal. Machine learning, when was introduced, allowed it to change this paradigm. So we don't need to explicitly tell the machine what it has to do, but we can retrieve from data the instruction. So there are three main types of artificial intelligence. Artificial narrow intelligence that is specialized in one area and solve a specific problem. Artificial general intelligence that refers to the computer that is as smart as a human across the board. And artificial superintelligence is much smarter than the best human brain. And it's, of course, not the case right now. But for sure, all the advancements that have been done are on the path towards artificial general intelligence. So the path is towards that goal. Right now, we are very expert in artificial narrow intelligence. And from 1915s, from the very start of when artificial intelligence born, actually we get different, we moved to machine learning, so learning from data, to deep learning. That means that we try to mimic as much as we can the brain function. And now we have seen the advancement of generative AI, so deep learning models that actually are able to create original content. Of course, this was possible thanks to the advancement, the technological advancement in the computing capability that allowed to develop all these models and doing all these steps. So I will give some brief notion on the main about machine learning and the main ingredient of machine learning. So machine learning needs data, and data need to be the good one for the task. So what I always say is garbage in, garbage out. If we give garbage as an input, we cannot expect any magic things as an output. So data selection and feature extraction are fundamental steps to get to our goal. Then we need to choose algorithm, because there are different algorithms available that optimize an objective function. That means that we want, in case, for example, of supervised approach, we know the target, and we have our data, and we can test different algorithms to see which one is the best to optimize the error between the target and the prediction. And once we use this algorithm, we can have our model and we can have our instruction that the computer can use to convert data into decision. The label is like just the prediction. Once we have the model that is working, thanks to the training phase, for example, we have our predictions. And so with new data, we will have our new prediction, new label. So there are two main types of machine learning. Let's say unsupervised and supervised. Most of you probably already know, but I just give brief overview. So actually, when we don't have labeled data, we have just our data without any label. We can actually see how different models can observe and learn from data. So in this case, for example, we have images with anomaly, with no anomaly. So the model based on an unsupervised learning model can learn to discriminate between classes based, for example, on similarity between the groups. And so we can have clustering problems solved by using this approach, where clusters are identified based on the similarity between the element inside in each group, or anomaly detection. Anomaly are identified based on the dissimilarity among data. And supervised learning models need instead labeled data. So we need to give both data and the labels. And thanks to this, they can try to find the best model to perceive the task, the goal. And we can have classification problem in the case we have discrete value. So if we want to predict the discrete value, that means if a scene contain, for example, a volcanic activity, an effusive activity, or like no activity at all, or regression, if we want to predict continuous value. And these are examples of traditional machine learning algorithm. We have super vector machine, for example, as a supervised learning algorithm. And actually, the goal of super vector machine is trying to find the best, the optimal hyperplane or set of hyperplane discriminated to class by maximizing the margin, for example, or k-means that try to find cluster in an iterative way by, I don't know if it's, okay. So iteratively, it try to find the best cluster of data by grouping based on similarity. That means the Euclidean distance of the elements of each group and the centroid that iteratively is calculated, as you can see here. And actually, we have talked about traditional machine learning model. So human experts determine the hierarchy of features to understand the difference between the data input. And actually, this traditional machine learning model respect the raw input, require a feature engineering phase. So the expert need to extract the meaningful feature from data that then can be used from the model to discriminate for the specific task. And this feature engineering phase is very, very important. It's fundamental because traditional machine learning models are not adapted to retrieve automatically from unstructured data features that are meaningful and then classify. Deep learning instead, it's a more complex model that actually is able to retrieve by itself feature from raw input data. Of course, the raw input data has to be chosen carefully depending on the task, but features are extracted automatically by the model, and the expert doesn't need to set the feature during a feature engineering phase. An example is a neural network, a simple neural network with one input layer, an input layer, and one output layer that actually is considered anyway a traditional machine learning model because it's very simple. It cannot be good enough in retrieving feature like it would a deep learning neural network. Because as you can see here, all the layers that are considered, all the neurons, step by step, try to replicate a bit like the brain human functionality of the vision system, where actually you try to retrieve a hierarchical feature that highlights specific part of the image. Like in this case, the input is George Washington, and for each layer you can identify the edge, the combination of edge, identify other feature, the combination of feature, and then you can label the image as a being of George Washington, for example. And actually what we use for our goal is trying to exploit this deep learning and machine learning model to get inside interpreted automatically data. And this field, from if you do that from images, this is called computer vision. So computer vision is a field of artificial intelligence that train computer to capture, interpret information from images, like human vision does. That there is an eruption, the human eyes look at the eruption, the brain processes the fact that there is an eruption going on and identify that there is an eruption. We try to teach the computer to process images that is come from a sensing device to recognize an eruption taking place as an eruption. And this, of course, allows to make automatic interpretation of data. And an example, one of the models that are the most used one for this task are the convolutional neural network, that actually are deep neural network that at the beginning allow to extract the meaningful feature from the images. Once you get, and this is done by using a set of convolutional layers that actually are used like special filters that replicate again how the human visual system try to create a hierarchical feature. And by using this convolutional layer, you actually can get a final flattened feature layer that actually is given to a classification part that work similarly to how a traditional machine learning model does. And by doing this, you can get the final target, like in the case for I showed you before of George Washington. So in this case, there is a volcanic activity in the image. And this is called image classification. So here we have a cat, and if we have a classification task, we can use a CNN, like the one I showed you before, that act as an encoder to recognize that there is a cat. So the output will be the label of representing what the scene contains. And there are examples like SquidNet, VGG16 are two kinds of architecture that are used as a CNN for image classification tasks. And if we want not only to label the image, but we want actually to find all the pixels contained in the, so if it's a cat, I want all the pixels representing the cat. This is called segmentation. And in order to do that, we need to add a decoder layer after the encoder that allow to enable precise location, like transporting like the convolution that had been done at the beginning. So it's like a symmetrical thing. So now we can see some example of how artificial intelligence can be used for volcanic hazard monitor. So the goal is understanding volcanic activity from space. And under this perspective, due to the variety of satellite data available, we can extract information of volcanic activity from data by using AI. That means we get our data, this data are processed through AI, and we can segment the image, classify the image automatically. So if there is an activity taking place, we can actually characterize the activity. We can say if something started, where it has started. We can characterize in space and time, but we also can extract knowledge from data. This because if we get lots of information, lots of data in time, lots of variable and parameter, we can try to use artificial intelligence, especially unsupervised, for example, artificial intelligence, to get information on, to get the knowledge from data. So patterns that maybe were hidden, unknown. Or we can forecast, for example, eruption, like by using a long short term, for example, architecture algorithm, we can actually forecast the eruption by retrieving specific trend that precede the starting of the eruption. So we explore how AI can help understanding volcanic hazard problem, doing this path. So from the forecasting to detecting, to tracking, to quantifying, nowcasting. That means before an eruption, we can have a subtle increase, for example, in surface temperature, and we can detect indicator of changes of some parameter like thermal emission. Then we can identify exactly when an eruption or volcanic activity is taking place. So when it starts, thanks to satellite data, and then once an eruption is in process, we can track the evolution of the phenomena. Then we can quantify thanks to all these parameters and characterize the eruptive product, and we can try to do short-term prediction of the evolution of the volcanic activity. So I will give an example of one of each of these steps. So for forecasting, the motivation are that why deep learning is important, because actually by using convolutional neural network, you are able to detect an anomaly, not just because of the intensity, because sometimes subtle anomalies actually can have the same intensity as other artifacts, like solar radiation, for example. So our goal in this work was trying to detect changes that were due to volcanic emission, for example. So we trained a model at CNN in order to detect an anomaly as a volcanic anomaly, not just because the intensity, but because it has specific features, for example, spatial feature. And as you can see in these images, with traditional technique for Tlochevskoy volcano, for example, by using aster data and just thermal images, if you use a traditional technique with intensity, you cannot get rid of the solar radiation, because actually the intensity was it was the same. So what you can see is by using the UNet, this is one kind of, is a particular type of CNN, we can actually detect just the volcanic related anomalies that that has a similar intensity respect solar radiation, but actually was related to volcanic activity. And by using this high level of accuracy, of course, you can actually detect changes and trends that otherwise were not detectable. And like all the other thing, for example, here you can see cloudy images that actually most of the time were like the anomaly was not being able to be detected, that is detected instead. So we can use also cloudy images because the model is able to recognize a volcanic feature, a volcanic anomalies. And this was used to study the volcano study case. So Volcano Island actually underwent the gassing crisis in 2021. And this crisis we were able to detect the increase in thermal change thanks to this kind of model. And also, like, beside the fact that we could use this model with cloudy images and being able to detect, like in the case of 2020, September 10, we were able to detect also change in thermal emission, like thermal emission close to the harbor. Actually, this was the case. So there was the gassing also in the Bahia of Levante was detected by our model. And then about detecting, we developed a model. It's a cascading architecture that was able to detect the start of volcanic activity with high accuracy, but also to recognize what was happening. So it is an extended anomaly due to effusive activity, or is an isolated anomaly due to strombolian activity. And this, of course, it's important in terms of volcanic hazard. So this cascading architecture, as you can see, is made by two parts. Model 1 is a CNN that actually has the task of recognizing the volcanic activity taking place. And the second part, it is a random forest that actually is able to map if there is an anomaly, the thermal anomaly, but also to improve the accuracy of the model. In this case, actually the main ingredients of the model 1 is that beside the input feature space that of course were chosen in order to highlight the thermal emission. So we use of course infrared bands. We also used visible bands in order to discriminate better between cloudy and also no volcanic activity images. We use transfer learning, that it's a kind of it's a learning mode that allows us to use a pre-trained model and being able to retrain a pre-trained model to a new domain. This allows us to save a lot in terms of time, because we don't need the same amount of data for the training phase. And so this transfer learning was very useful in our case to be able to speed up the entire process. And then the other ingredient is the ensemble architecture. If you use more than one model for a specific task, you can combine the output and have a more robust output. And after we apply this model and we get our result, we apply a random forest model that is a group of decision tree. Most of you probably know the decision tree is like a set of tree. A decision tree it's like mimic what is the if-then rule. So based on the input, it creates a set of rules during the training phase that allow you to classify, in this case, a pixel, if it's anomaly or not. And by using a random forest, you make an ensemble. So use lots of decision tree to get a final output that is a statistical measurement of all the trees involved. And this kind of model actually is very precise because it's a pixel-based one. So what we do is, if the prediction of the model 1 is confident enough, that means that the output of the model has a high percentage of accuracy, because for each model you get a percentage of being one of the class of the target. Like if we have, in this case, we have 4 classes, as we have seen before. We have no volcanic activity, isolated activity, extended volcanic thermal anomaly, and cloudy sky condition. If each of them if one of them has a probability output greater than 85%, this output is reliable. If not, that means that we need to undergo a second step that we call check and revise. So in this case, we use the model 2 random forest to see if there is actually an anomaly or not. So we go more into details of in the scene, and this allows us to increase the accuracy, and get accuracy of 98%, 95%. And this is like from detecting to tracking. Once an activity was detected, we can track that. Like in the case of La Palma, we detect the start of the effusive activity, and we were able to follow the evolution of the effusive activity. And so we were able also to quantify the extension of the lava flow and see all the duration of the effusive activity. The other volcanic phenomena that we can track by using this approach, this advanced approach, are, for example, the volcanic cloud. So actually, as we have seen before, volcanic cloud, like different components of volcanic cloud, have different spectral signature. What we know is that at 10.8, there is the absorption, the ash absorb more than SO2, for example. So what we can say is that if we combine the infrared tear bands such that we can highlight the presence of ash, SO2, or all the rest, we can actually create an image that can be used by a deep learning model, for example, to automatically detect the volcanic cloud. So what we do is we create what is called ash RGB composite. This is made by a red channel that is given by the difference between the infrared channel at 12 and the infrared channel at 10.8. The green channel is the difference between 10.8 and 8.7 because it absorbs more than 8.7. And then the free channel, the third channel, the blue channel, is the 10.8. That is related to warm clouds, warm surface. And by using this as an input, as you can see, we can actually develop a model, and we did that, in order to detect the presence, like all the pixels belonging to the volcanic cloud. So we can segment an image. And by doing this, of course, we can isolate the volcanic cloud from all the rest. And what we can do as a post-processing step is, okay, now that we have isolated the volcanic cloud, we can actually train a model that is a traditional machine learning model, the one that is easier to train because it needs less data for training. We can train a super vector machine to identify if the volcanic cloud contains ash, SO2, or mix, or is background, like the background in this case is not present because it's already cut back from the deep learning model. But as you can see, in this way, you can actually characterize the qualitatively, of course, the components of the volcanic cloud. And this process is very important because for different reasons. Of course, the aviation, we need to communicate the direction of the volcanic cloud, if there is ash, because ash is a problem for aviation, etc. So actually we can monitor the evolution. We can track a volcanic cloud. Sorry. We can, there's a video. Okay. So we can track the volcanic cloud in near real time once the image is available. In this case, we have used a severe image because it's geostationary satellite data that allow us to monitor the dynamic of the phenomena. And so we can actually see how the volcanic cloud spread in near real time and how it is composed. If ash, SO2, or mix. Oops. Then we can quantify. That means we can actually, once we process all this data, we can characterize all what is going on. So this is an example of Etna 2022, 2023, and where we actually were able to assess the active area of the lava flow, the crater that were active, the length and the altitude, the lowest altitude reached by the lava flow front, the effusive rate, and the volume. And then we can nowcast, so we can make short-term prediction of the either volcanic activity of the volcanic phenomena. So in this case, I can show you that we have created a model like the LSTM, long short-term model, that allow to catch short and long-term dependency in the variable that allow you to make a prediction, a short-term prediction of the evolution of the lava flow. And this allowed us actually to, this worked very well with effusive activity, and also we are able to reconstruct signal where actually the signal was obstructed by clouds, for example. And the other nowcasting that we can make is nowcasting of the lava fontaine eruption. So after we are working on this, these are like the work in progress because we already presented interesting results because actually the volcanic relative power present a very clear sign of changing sign before a paroxysm event start. So if we train a model, a machine learning model by using the right feature, like statistical feature of the signal of the volcanic radiative power, we are actually able, as you can see in this case, to forecast the lava fountain start, because the trend is very neat, and actually we have shown that there are these changes are detectable by a model. And all of these, of course, contribute to what we call AI-powered volcanic hazard monitor from space. So by integrating all these and by using all the output of this model, we can actually assess the activity status of the volcanic activity status. So all of this to tell you that if we can use satellite and we can automatically detect the forecasting, we can detect the start of a volcanic activity, and we can track the evolution of volcanic phenomena, and then nowcast. Actually, we can, by using satellite data and artificial intelligence, we can improve a lot in this sense. We can enhance a lot volcanic hazard modeling from space at global level, and this is our final goal. Of course, I talk also for all my research group team that is made by Ciro Del Negro, Vito Zago, Eleonora Amato, Simona Cariello, Federica Torrisi, Giovanni Di Pella, Arianna Valloguti, Alessandro Laspina. And I thank you all for your attention. And if you want more details, contact me, of course. And also with this QR code, you can actually visit our main page where that is updated continuously. Thank you.
Thank you, Claudia. That's a great presentation. And now we're open. We have some time for questions. So if anyone has a question, feel free to type it in the chat box or maybe unmute your microphone and just say it out loud. Okay, I'm gonna throw the first question in this case. I'm wondering, all these models that you have shown us are trained on data specific for Etna. How feasible is it to use data from other volcanic or other volcanoes to um, generate similar models?
Yes, so actually, not all the models I showed you are trained on Etna, but I'm sorry I didn't specify because I wanted to give an overview of all. But so the volcanic cloud model, for example, was trained on Etna with Severi. And so that is specifically for Etna, but we tried to actually expand and apply the model to Shishalding, for example, in Alaska. So a completely different model. And by doing some adjustments, so by retraining on both the model was working very good. And so this is something that for sure need to be addressed, because our model, we want to build models that are applicable to like worldwide. And I can tell you that the UNET model, so the one for forecasting, was applied to 80 different volcanoes. The same for the cascading was applied to lots of different volcanoes all around the world. Like we try to pick, of course, the ones that were more different in terms of activity, of latitude, of condition, in order to make the model more general, as general as possible. And for the forecasting, for example, Volcano Island wasn't used for during the training phase. And so it was very interesting, the fact that that kind of model, regardless the fact that it wasn't trained on Volcano Island, was able to detect the increase in thermal anomalies of the fumarolic, because the volcano actually just has the gassing activity, so very subtle thermal activity, and was able to be detected. And that was a very good result, for example.
Yeah, that's very interesting. So there's a question by Ivan Granados. In the case of the last unrest of Vulcano, this analysis allowed you to track the degassing extension out of the La Fossa crater?
Yep, exactly. Yes, like the Baia di Levante. So where actually we detected, so not in the, because we of course detected the anomaly in the fossa, but we were able to detect also in Baia di Levante, that is like the upper north part, like the north part, where actually the gassing activity was taking place, and this was a very very good results. Yeah.
Okay, another question by Michael Murphy. How much computing power is needed to run these AI models on a local and or global scale?
Yeah, it depends on the model. Like there are models that need to be run in like machine with GPU, for example, and other that are easy, like traditional machine learning model can be run even in like with by just using CPU, for example. And anyway, the good thing is that once you train your model, the model trained can be applied with any machine, because the most time consuming phase is the training phases, unfortunately. Yeah.
Yeah, that's interesting. If you have a model that requires a lot of resources for training, then
Yeah.
we
Yeah.
sorry, we're able to run it on like maybe a volcano observatory that doesn't have those resources, but since it's already trained, it doesn't require all this.
Exactly.
Right.
Yes. Yeah, the most time consuming part is the training phase, because depending on the model, it can be very, very time consuming. Deep learning model require lots of data to be used, and they are lots very complex, because as I told you, like they need to extract features, and that part is very time consuming. But once the model is trained, actually, we have seen that there is like even saving in time respect other approaches. So yeah.
Awesome. Is there any other question in the audience? Darren has a question. You can go ahead.
Hi, Claudia. Great talk.
Hi, Devin.
Hello from Alaska. I
Hi,
no,
how are you?
I yeah, good. How are you? I have
Hi.
yeah, so my question is, of course I've seen this presentation in some way before when you and Federico were
Yeah.
here. I'm curious if there are any plans to incorporate like wind models and wind speeds to kind of automatically quantify SO2 emission rates, because I know there are some bands in your volcanic cloud model that look at a number of pixels of SO2, but I don't know if some level of quantification is possible.
Yeah, actually, we worked on volcanic cloud on SO2 quantification using Tropomi. So because it's the one that give you an estimate of SO2 content. So quantitatively is the one that is the best for this task. And but I didn't present this here, but with Tropomi we correct for altitude in order to account for the altitude correction, and to have an estimate, a quantitative estimate. But using volcanic cloud with Seviri, with thermal, what we are doing now is not about quantification. So beside the number of pixels, we are not quantifying, so we can actually assess the level of content of ash, for example, based on the level of redness, for instance. But what we are working right now, that it's our main goal, it's trying to nowcast the dispersion of the volcanic cloud. So actually, we are working right now on creating a model that is like a convolutional LSTM model. So a model that accounts for space and time with Severi in order to predict the evolution of the lava flow. This model would account for wind, would account for velocity, because the model automatically retrieves this information, because you give seeds, like satellite time series images. So it's all of this information, it's accounted by the model to have an idea on the wind, on the velocity, and so this is what we are working right now. Right now.
Oh, cool. Thank you. I look forward to seeing a publication coming out of it.
Yeah.
Thanks.
Welcome.
All right. So yeah, we made it to the end of our session for today. Thank you once again, Claudia, for that amazing presentation.
Thank you.
We're gonna be posting this recording for today's session online, so keep an eye out. And remember, our next session is gonna be on March 25th at 4 p.m. Eastern Daylight Savings Time in the UTC -4 time zone. So hope to see you there. Thank you everyone for joining us.
Thank you, Gustavo. Thank you all. Bye.